This is really about a technique that has developed quite nicely over the past few decades. I'll get to mention a few things that happened recently, not my work, but some exciting developments. So before I tell you, talk about the technique, maybe I'll just mention some inequalities in high dimension, which I think are interesting anyway, and they were formulated in various contexts and so on. Some of them are known to be true and some are conjectures. Okay, so yeah. So these are inequalities in high dimension. So typically the dimension is allowed to go to infinity, but we do want to understand the dependence on the dimension, if any. So yeah, okay. So I'll mention, there are many to choose from. I picked 8 for their diversity. Please feel free to comment. I will just go ahead and state each one and mention a little bit about it. Okay. They do have something in common. So the first one is called slicing. This says the following. So you have a convex body K in, let's say, Rn. So by body, I just mean that it's closed and bounded. And then convex, yeah. So if X and Y are in the set, then the segment is also in the set. Okay. Okay, so here's the statement. If you take a convex body K with volume 1, then there exists a hyperplane, an n-1 dimensional hyperplane, H, such that volume of K intersect H, so this is n-1 dimensional now, so n-1 dimensional volume is at least a universal constant. So C is a, small c's, big c's will all be universal constant. Okay. So this is the first one. So this is an inequality, right? Under this condition. Okay. Right? I mean, it's an inequality for every convex body, in any dimension. The second one, so this was formulated by Bourgain. And who at the time was able to show this to be 1 over a polynomial in n to the 1/4, okay, times a log factor. Okay. As of a few months ago, it's fully resolved. So this is true. This is a true statement now. You'll see more or less all the techniques involved. Okay. The second one, which came a bit later, is called the thin shell inequality or hypothesis or conjecture, and a universal constant. So we don't know what the actual value is, but it might be 0.1. Yeah. No. I mean, simplex is a one that we don't have something worse than, but it's not conjectured for any good reason. Yeah. No. Yeah, there exists. Yeah, it's true. and you don't have to take my word for it. but please, please do be skeptical. Okay, so as I go along, I'll introduce some of the definitions needed for the tool as well as for the statement itself. So The next one that's useful is the notion of distribution being isotropic. So to state this, I want to say that a distribution in Rn, let's say nu, is isotropic. And if the expectation, the mean, according to nu, is 0, and the covariance is the identity. Okay. So this is just a normalization. And if you take any distribution that has bounded second moments, bounded away from, bounded by some, it's not infinite from above and not 0 from below, then you can apply an affine transformation to make a distribution isotropic. That's one. The second notion, which is also going to play a role in many of the conjectures, is the notion of a log concave distribution. We say that a distribution, or let's say a function f Rn to R non-negative, so it's a non-negative function, is log concave if basically the log is concave. So explicitly for all xy and for any t scalar in 0, 1, the function value at the convex combination tx plus 1 minus ty is at least, so concave would say it's at least the average of the function values at x and y. This is log concave, so it's f of x to the t, f of y to the 1 minus t. So that's a function being log concave. And so a distribution is log concave if its density function is log concave. It has a log concave density. It's a distribution Rn. So now, here is the inequality. For any isotropic log concave distribution nu, the expectation of the length of a random point, so from nu, you draw a random point, you look at its length, compare it with square root n, and look at the square. So the variance or the square deviation of x from root n is bounded by a universal constant. Let me just justify what this is and draw a picture. So this is just a Euclidean norm. If a distribution is isotropic, then the expectation of length of x squared is the, under nu, is the trace of the covariance matrix, right? Because the trace gives you the x1 squared plus x2 squared. And we said it's isotropic, so this is the identity matrix, so this is n. So you see the expectation of x squared is n. So x is like root n, and so we're comparing the deviation from root n. But this is very nice because what it's saying is that, I mean, no matter what your distribution is, remember, in particular, important useful thing to note, convex bodies, the indicator function of convex body is log concave. Right? So if I take the function f of x equal to indicator function where A is a convex body, then this is log concave. Just so you're fully convinced. I mean, you just need to check this condition, right? So if the points hit 0 outside and 1 here, the function. If it's outside, there's nothing to check. If it's inside, it's clearly true. If it's crossing also, it's true because you get to take the smaller value. Okay. So in particular, uniform distribution can be made isotropic by this. Great. Now, what is this saying? You have the center of gravity, which is 0, and you consider a ball of radius root n. Right? This is a wall of radius root n. And the variance from this is constant, which means that if I go just a constant more, then I've captured, let's say, half the mass, or 0.9 of the mass. So most of the mass of this convex body, which is an arbitrary isotropic convex body, is contained in a shell of constant thickness. Right? So that's what the thin shell conjecture says, that most of the mass is contained in a thin shell for any isotropic log concave distribution. This is still a conjecture. Okay. But there was some remarkable development recently, late last year, and the current status of this is that this is we don't know that it's dimension independent, but we know it's bounded by up to a constant by log n. Okay, so that's the second one. And then comes the next one, which we can all take credit for. It came from computer science and was formulated in the analysis of an algorithm. It's the following inequality. So let's stick with isotropic. We have isotropic, either convex body or log concave distribution nu, right? Not writing log concave anymore, but I'll mention when it's more general. And this inequality comes from a classical consideration called isoperimetry, which we have seen several times in the talks in different contexts. And the basic issue is, what is the minimum possible ratio of the boundary of a subset to the size of the subset, right? Just like graph expansion or other weighted conductance. You want to know, you have some measure now. I pick a subset S, and I want to know what is the measure of the boundary compared to the set itself, and how small can this be? Now, this only makes sense if the complement and S should be compared. So really what I'm looking at is, just like in graph expansion, the minimum of this and the complement. And again, here by this we mean the n-1 dimensional measure. So if you have a density, it would just be the integral over the sets on the boundary, and define these things formally, but not too much about it. Okay, so even in the uniform case, this makes sense, right? You have some convex body and you're asking, what is the subset that minimizes the ratio? Okay. And so the inequality says that for any isotropic convex body and for any subset of this, let's say I'm formulated, of course, log concave is more general, but sometimes more illustrative with convex bodies. The volume of this boundary, right? This boundary is at least constant times the minimum of the volume of S and the volume of the complement. Sorry, I'll truncate this. Volume of A minus S. Okay? So this expansion is a constant, independent of the dimension, independent of the convex body, under the assumption of isotropy. Now, well, this I was saying for a general measure, so whatever is yeah, I could say that here also, but it would be, yeah. Okay, now there is a version of this that's useful to formulate, where we can write it without the assumption of isotropy. And for that, we say, so suppose now you take a distribution nu that's not necessarily isotropic, but it's log concave. Log concave. Then let A be its covariance matrix. So A is the expectation of X minus whatever is the mean. So let me call it mu times X minus mu transpose, okay, the covariance matrix. And so the way to write this more generally, and this is another high-dimensional inequality, right, is that this is at least a universal constant over square root of the operator norm of this, the largest eigenvalue of the covariance matrix, times the same minimum of volume of S. So since I'm writing log concave, let me write here nu of this and nu of S, nu of Rn minus S. Okay, that's the conjecture. I'm sorry? I can scale up the operator norm. Yeah. And that will make the expansion worse, right? Because if you look in that direction where you're scaling up, the surface area is staying the same, the volume is going up. So it does the right thing. It's just linear, so it cancels out. Perfect. There's no difference on the ratio with the condition number. No, just the top eigenvalue. Yeah, that's right. Yeah. Because we're asking about a lower bound on this, right? So, yeah. Right. Now there is a nice geometric interpretation of this as well, which is the following. And actually, so there is a family of subsets for which this is true and tight. Anybody want to guess what those subsets are? Hyperplanes, right? So, or half spaces. Subsets are half spaces. Then this is true because in particular, let us look in the direction of the maximum eigenvalue, that eigenvector direction. And in that direction, okay, the projection of a log concave. So these are nice properties that are follow from the definition plus some nice structure. The projection of log concave remains log concave, right? Something that we use and enjoy a lot for Gaussians. It's also true for log concave. And the point is that the covariance matrix is already telling you what the variance is in that direction. And so the projection looks like this, let's say in some direction. And if I look at the projection of the distribution, maybe it's something like that, right? And in this direction, we know we picked it because it has the largest variance, which is the largest eigenvalue here. And the point is that for a log concave distribution, the isoperimetry will be 1 over the standard deviation. Just think for Gaussian, right? It's 1 over the standard deviation of the Gaussian. It's just like that. The reason is simply, once you go 1 standard deviation out, the measure drops off very fast. So the measure is basically proportional to standard deviation times whatever is the cutting area of the surface. So you're done. So the area of what you're cutting divided by the volume is constant over standard deviation. So this inequality is simply true if you only consider half space cuts. Because in every other direction, this is only smaller. But the conjecture is that half spaces cuts are nearly the worst possible, up to universal constant factor. Okay. How's that for an inequality? Yeah. Okay, so this was formulated by Anand, Lovas, and Ramanujan, 95, and led directly to better analysis of random walks for sampling high-dimensional distributions. One thing they proved here, so this is a conjectured inequality, a true inequality, which is also tight, right? It may not be in this form, but it's tight, and we don't need to look at covariance or isotropy. It says that for any convex body K of diameter D, right? This ratio, this isoperimetry, is at least 2 over D. So in place of constant over the operator norm, we're putting 2 over the diameter. Okay. You can see that operator norm cannot be more, the covariance matrix cannot be more than the diameter. square, right? Because no point can be longer than that. Even the trace is at most the diameter square. So, but the point is, so this is a true theorem here proved by them, and this is tight. So just to see that example, if I take, for example, a cylinder of let's say length d, which is approximately the diameter also. I could make it lower dimensional, and you cut in the middle, then the area we're talking about is, say, some A, and then the volume of one side is A times d over 2. So this is exactly 2 over. So it's a tight theorem. And we will prove this as one of the exercises. Yeah. Okay, that's 3. Now, this isoperimetric notion is, of course, related to classical things. It's so natural. It's related to what's called the Poincare constant, the constant for the Poincare inequality, which is formulated in a completely non-geometric, sort of more analytical way. And it says that for any distribution, say nu, and now it doesn't even have to be log concave. So for any distribution, you can define what is a Poincare constant. So for any nu, this is defined as follows. For every smooth function f, so the derivatives exist, the variance under nu of f, so the expectation of f minus the average of f square, is bounded by this constant times the expectation of the gradient of f norm square under the same nu. So it's saying that the variance in f, how much f varies from its mean, is controlled by how large the gradient is on average, which kind of makes sense, right? Locally, you change as much as the gradient, but of course, it's not going to be the case. I mean, in general, gradients can vary a lot, but if you can put a constant here that makes it true, that's the Poincare constant. Now, for log concave distributions, for log concave nu, we have that the Poincare constant is just equal up to constant, so up to universal constant, to the inverse of this isoperimetry squared. So let's call this 1 over psi, okay, this minimum. And so this is just psi squared. Okay. So one way to formulate the KLS conjecture is that for isotropic log concave distributions, the Poincare constant is a constant. Okay. This equivalence is one direction is always true, meaning if you have Poincare, it implies isoperimetry for any distribution. The other direction uses log concavity, the equivalence. Yeah. Okay, so that's this. Good. I'll continue there. Sorry. I guess. Yeah. Now we'll move to a slightly more probabilistic view, and this is about concentration. So this one says that, again, we have an isotropic log concave nu, then the probability that the length of x, which we said is about root n, right? The probability it exceeds, say, some constant times root n, p greater than 1, is smaller than e to the minus constant t root n. You see this? So root n is what you expect. The probability you're more than 2 root n is already sub-exponentially small. Okay. In fact, it's not known if this is the best possible bound. For Gaussians, we will get here an n. Okay, and it's possible that this can be improved as far as we know. But this is a true theorem, and this was a highly non-trivial statement first obtained by Powers. Now, the next one allows me to introduce an important special case of log concave distributions called strongly log concave. Again, we saw these in Pravesh's lectures. Let's say nu is T strongly log concave. And this just means that the density function has a Gaussian factor in front of it with a T coefficient. Oh, sorry. So it looks like nu of x, if I'm using the same notation for the density and the yes, yeah, n, yeah. Yeah, so the thing just gets squared. Yeah. Yeah. Even for strongly log concave, we will get that with the additional factor of, sorry, I'm using that same t, but let me call this alpha here, because this is I'm learning from previous speakers. But let's say if nu x is e to the minus t x squared over 2, this is what we mean, times some other, say, nu 0 of x, which is also log concave. So as long as your density looks like this, it's whatever log concave times a Gaussian with a t here. That makes it t strongly log concave. When t is 1, it's strongly log concave. Okay. For these distributions, a lot of things are known. In particular, they behave like Gaussians in many ways, in terms of concentration, and notably for isoperimetry. So if I look at this the nu of the boundary of any set divided by the smaller of the set and its complement, then this is now not only is the conjecture true that it's a constant, you don't even need isotropy, it's actually at least square root t. Okay. So in particular, if t is 1, if it's a strongly log concave distribution, then the KLS constant and the Poincare constant are a constant. But even if it's not strongly log concave with t equal to 1, let's say t is some parameter like 1 over log n, you'll still get something highly non-trivial. Now, in fact, something much stronger is known. Yes, so the concentration here, instead of being like this, would be e to the minus t alpha squared n. So now I'm talking about an even stronger version of this. So that I don't have to keep writing the min, let me assume that nu of s is less than half. Okay. Then there is a stronger isoperimetry one can formulate, which says that nu delta s over not just nu of s, but let's multiply this by a factor of square root log 1 over nu of s is actually at least square root. And this is the log Sobolev constant in this case. For log concave distributions, this isoperimetric ratio is the log Sobolev constant square, but you know, I mean, this square is the log Sobolev constant. But in general, you can formulate log Sobolev like we did Poincare with a similar inequality for all smooth functions, except on the left-hand side, instead of variance of f, you have entropy of f. That's it. Okay, here is so this is a theorem, right? This is we can prove in multiple ways. We will prove it today as well. Yeah. Okay, that's 5. 6, still concentration, but in a very different context. This is a named theorem. It's called Carberry-Wright. It's about the concentration of polynomials. Okay. So you have some, I'll give a basic version of it. A polynomial p of x of some degree D. And its domain, we're looking at X in a convex body over convex body K. Okay? Yeah. Yeah. I mean, it's much more general, right? The actual form of the density can be anything. So for example, take a Gaussian and restrict it to a convex body, arbitrary convex body. That's one strongly low concave. But that distribution is, quite a huge family of distributions, and you won't have some of the, it's not a product distribution, for example. Yeah. So degree D or K, and this is about not concentration, but anti-concentration. You want to say that the polynomial cannot be too focused. It's got to spread out. So one way to formulate is that for any, I used T here, but I will not use T. For any Y, okay, probability over K, so you're drawing X from K, and you look at the polynomial value, and you ask, what is the chance that P of X is not this value Y, right? It's away from this by some epsilon, right? No, I'll formulate the other way, but the point is anti-concentration. What's the probability that it's close to this? We will say this probability is small, so that with large probability, you're away. And since this holds for any Y, this means it's not concentrated anywhere. And so this is bounded up to a constant by the degree times epsilon to the 1 over degree, as long and the degree of the polynomial. I'm sorry. Yeah, that's it. Actually, under the assumption, one assumption we have to make, that the variance of this, the expectation of over K of P of X squared is 1. I could move this into the right-hand side bound, but so assume that the second moment of the polynomial is 1. Of course, you have to do something like this, right? Because if the polynomial has extremely tiny thing, it can be concentrated. So as long as it's this, it cannot be close to any one value. And that's what this is saying for arbitrary convex bodies. This has turned out to be useful in surprising contexts. Yeah. Okay, that's number 6. You will see essentially how to prove 6 also. I mean, really, so the point by now, as you might have guessed, is that all the inequalities here, both the true ones and also the state of the art for the bounds that are the best known bounds, are proved by the technique that we'll discuss today. So, yeah. The next one is a much more general thing, and really it deserves its own set of lectures. So I will only just mention it briefly. Today we won't have time to look at it, but it's an inequality again. And this is inequalities for Markov kernels or transition operators, right? So it's just like saying if it was a Markov chain on a graph, then the next point is P transpose X, the next distribution. You keep applying that to get the next distribution. That's your transition matrix. But in general, this could be an infinite kernel, right? Each point, you know what the distribution is for the next point. Okay, and important quantities here. Maybe it's not even. Maybe I won't even define both. But basically, for a Markov kernel, you can define what the notion of a spectral gap, which, like Poincare and log Sobolov, is an extremum over smooth functions. It's an extremum over smooth functions, and similarly, you can define the log Sobolov and sometimes the modified log Sobolov constants of this matrix, basically not matrix, but it's a pairwise operator, and now, depending on the context, the family of transition operators, there are inequalities. Let's say the spectral gap is at least there's something, and the log Sobolov inequality is at least something, and there are quite general families for which we now have fairly tight bounds. For example, the Glauber dynamics on the hardcore model for graphs, if you know what that means, right? The proximal sampler for strongly log concave distributions. And for these, at the end of the day, to show that these kernels are rapidly mixing, you have to prove an inequality like this. And the reason I'm mentioning it here is that to prove these state-of-the-art inequalities, the technique is, again, localization. Okay. And then the last one is certifiable hypercontractivity. So this is yeah. So rather than all smooth functions, we'll restrict attention to a family of interesting functions, polynomials. We did that once before, but now it's a different thing. And so let's talk about functions f of x defined like this. So first you append a 1 so that you allow yourself non-homogeneous terms. And you power this k times. So this is the kth order tensor from this, right? So this is a kth order tensor. And now you take the inner product of this tensor with some fixed tensor of the same dimension. So that's a polynomial, right, of degree k. And the point is this: the inequality hypercontractivity is that the variance over a given distribution D, so I could call it nu yd, of f, okay, so for this family of functions, is bounded by, so for, now we're talking about new log concave, right? So log concave nu bounded by universal constant k to the k is this degree, times the Frobenius norm of A squared, 2k, yeah. Get this. Okay, Frobenius. So this is such a statement we saw yesterday. Pravesh proved this for the spherical Gaussian, in particular under concentration bounds. And there C was a constant, absolute constant. But whatever it is, this constant will show up in the degree of the polynomial you need to consider in the SOS, right? Whatever it is, it will be that will show up in the degree linearly. So your SOS algorithm will have an exponent that is basically whatever is the degree of the polynomial squared, I suppose, times this constant. So now, this is the inequality you would like. The conjecture is that this is actually a universal constant for every log concave mu. We know already that C is less than CPI for mu. We already know that C is less than the Poincare constant, right? And for now, oh, I didn't mention to you, the best known bound on the Poincare constant or on the KLS constant is, so for Poincare, the best known is log n. And so KLS, it's root log n. And so the best known we have here is not constant, but 1 over root log n. Okay, so for an isotropic, yeah, instead of this C here, what we know is 1 over root log n. Okay, so, but there are two things that this is true. We're asking, is this true directly? Right? Independent of this. And maybe this is true for much more general families. I mean, this is nicely formulated here for log concave. There's a natural reason to believe it's true, but maybe it's true. Okay, so that's the 8 I have here. There are many others. I'll just mention some names. So you can use the method we'll discuss in detail now to prove the self-concordance of barriers for optimization. You can use it to analyze what's called simulated annealing. The actual analysis depends on the localization method. There are many others coming up. I will mention at the end of the not this hour, the next hour, two applications that are unpublished, which you might find interesting. Any questions? I remarks or yeah. So the degree has to be smaller than the dimension for this formulation. If the degree is bigger, you get a different bound on the right hand side. Yeah. Yes. They formulate it more generally. It's, you know, I am talking here about a polynomial that's mapping to reals. You could actually have more general space, and then you can have a norm over that, and so on. The core is yeah. I'm sorry. Yeah. How is it related? Good. Sorry, I should have mentioned that. So these first three are monotonic or increasing sequence in the sense that whatever is the KLS bound directly is a bound for thin shell, and whatever is a thin shell bound is a bound for slicing. These were known for a while now. Yeah, so it's stronger. In particular, if you take, in the thin shell case, all we care about is the boundary of spheres, spherical intersections. If you take that and apply KLS, you'll get the thin shell bound. And going from thin shell to slicing takes some more work. This was a paper. Oh yeah, why is this true? Oh no. This variance, right? We're squaring things. Yeah, there. That's why we took the square root. There, it's yeah. Yeah, we saw this, for example, also in the monotonicity talks. You know, you get the square root is the correct thing. So you're saying that there is a hyperplane with very large. It's not. Yeah. I mean, the conditions are slightly different. This is just volume was one, so it's formulated. But indeed, there is a reason. Right. Yeah. We can restrict attention to isotropic things, and then a similar formulation still. But we are trying to prove that the surface area is large in general. Yeah. Okay. Oh, great. Did I take? Okay. So, okay. I have trouble with half. Perfect. Great. Among other things. I'll keep it there. Now, here's the point where I wasted a lot of, yeah. Oh, that's yeah. Huh? He's just asking what is the fraction of directions for which you expect to see a constant. At the moment, we can only. Yeah. Right. No. Remember, all we want to prove is that there exists one. No, we don't know it. We didn't know it for isotropic either till. Yeah. So let's see. Is there an equivalence? I mean. If it's isotropic, you're right. If it's isotropic, actually, every hyperplane through the center of gravity has volume constant fraction. That's just it follows from that, right? So the point here is that it's an arbitrary position. Right? Once you have a direction in which the variance is 1, then the surface area, the density has to go up to a constant at least. Okay, so now I have sort of this I want to do two things. I want to introduce the localization lemma, the classical one, and apply it to prove this 2 over d inequality. Okay, so it's an isoperimetric inequality that's tight, and now sounds silly, but I don't know which order to go in. Should we start with the inequality and then the localization lemma becomes a natural thing that comes out, or should I just state the localization lemma because you may not care about this application and then go from there? That's a different question altogether, but I was planning to write 3. Yeah. Okay, I guess I should build some intuition instead of stating the lemma straight. My only concern is that I should give you something useful before the end of this hour and a half. So I'll state the lemma here, only one version, and then we'll get back to how it comes up in the proof, and then also show equivalent versions that are sometimes more convenient. So here is the localization lemma due to Lovász and Šimanovič in 93. And the way they state it is the following. You have 2 functions, let's say g and h in n dimensions. And they, you can, for the purpose of this talk, you can think of it as continuous. And indeed, in the proofs, we really work with continuous functions. But the full generality is that they are lower semi-continuous. And then let's say they satisfy the following. That if I look at the integral of g, and by this I mean the integral over Rn of g of x dx, I won't write all that, but this is what we mean. This is positive, and so is the integral of h. So this is the assumption. We have 2 functions, positive, negative, they're lower semi-continuous, and they're positive integrals. Then there exists what's called a needle, which means, it just means 2 points in Rn and a linear function from 0, 1, a non-negative linear function from the unit interval, on the unit interval, such that so let's call this needle n. There exists a needle. N just means these 3 parameters, 2 parameters and a linear function. The integral over the needle, by that I mean, so let's just a little definition here. The integral over needle of a function is just the integral from 0 to 1 of f of 1 minus t times a plus t times b, right, times the linear function at t to the n minus 1 dt. This is the definition of the integral over a needle, right? It's you have 2 points a and b. You're going from a to b. You're just integrating along that line, except each point is getting weighted by this linear to the power of n minus 1. I'll draw a figure of this in a second. I'll just finish this. Integral over this needle of g is greater than 0, and integral over this needle of h is greater than 0. That's the whole theorem, the lemma. Okay. Huh? Linear, yes. Yeah, linear. So let's draw a little figure of this needle. So you have 2 points. Okay. A and B. So here is A, some B. This is your, right? Now what is this doing? At each point, you're getting this weight which looks like LT to the n minus 1. So imagine I draw a ball of radius LT at the tth point. So when t is 0, which means I'm at A, I draw a ball of radius L0. Okay. When t is 1, L, which means I'm at B, I draw a ball of radius L1. It's a linear function. So if I draw a ball of radius L everywhere, it will be exactly like this. Okay. And so you are integrating along this line. At every point, the weight is the cross-sectional ball. What is this thing? This is a needle. I mean, I broke the needle, but otherwise it's a needle, right? That's what. So you have some integral in high dimension, okay? Two integrals that are both positive, two functions with positive integrals. You can go down to an interval or a point, so which is included here when A is equal to B, such that you must have positive integrals for both with this weighting. So you get this additional thing. It's not true that there is some line on which the positive integrals exist, but there is a line with this linear to n minus 1 weighting for which you get this. I mean, whatever you wanted to prove in n dimensions is now localized to the neighborhood of, or not even a neighborhood, a weighted one-dimensional support. That's what I mean by that. Yes. No, they're arbitrary functions. Yeah. It's much more intricate for versus yeah. I mean, for one, there will always be one point where it's positive. So you're done. There's going to be a point where it's positive. Yeah. 2 makes it very interesting. Yeah. Sorry? Yeah. Yes. So if you go to K inequalities, in fact, and I'll formulate such a version, you can go down to the support being K minus 1 dimensional. But after being K minus 1 dimensional, it can be an arbitrary convex set. Or something that, maybe it's true. There is no theorem asserting this, even for, let's say, 3. So we know that the support cannot be lower than 2-dimensional in general, but yeah. Okay, we'll see other formulations. So we'll keep this in mind. I will not erase this for the morning. And now let's go to the theorem I want to prove, which is the following, and then I can erase that. Theorem, I have a convex body K and a partition. I'll formulate it in a way in which I don't have to deal with lower dimensional volumes. Partition, but it's equivalent, S1, S2, S3 of K, right, into measurable sets. Right? They all have volume. Then, so this is for any convex body, for any partition, the volume of S3 is at least 2 over D times the distance, an Euclidean distance between S1 and S2. So this is just the minimum distance between S1 and S2 times the minimum of volume of S1, volume of S2. Okay. So in particular, if I let the distance go to 0 and divide by the distance, that recovers the surface area on the left-hand side, and we get this 2 over D. But this is actually slightly more general, you could say, but it's not really. Because if you had that version, what you could do is you just apply the inequality up to distance, whatever is the distance D. So they're equivalent. Okay, so let's try to prove this. Okay, so how do we prove it? So really, you'll notice this is 2 inequalities. Right? You want to show that volume of S3 is bigger than this times this, and volume of S3 is bigger than this. Both have to be true. Min. Good. Right. One of them, right? So let's assume the inequality is false. So suppose false, right? For the purpose of a contradiction. Then there are 2 inequalities that are true. Pravesh is still completely. Which year of the PhD are you in? 3 is less than or equal to. And let me call this entire thing here. Remember S1, S2, everything is fixed. So this is some, let's say small a. It's just a scalar times volume of S1 and okay. This actually strictly, because we said that this is false, so these two strict inequalities are true. Now let me formulate this as G and H, right? So G will be the A times the indicator of S1 minus the indicator of S3. And H is A times the indicator of S2 minus the indicator of S3, right? And then these inequalities are the same as saying integral of G is greater than 0 and integral of H is greater than 0. Okay? So now we apply the localization lemma. Okay, no, I don't want to do that. Let's try to see what we can do. I want to simplify the picture here. Okay? We could just apply it and then but no, and it's all magic. Let's see how would you prove? I mean, sure, it looks like this, but how do you do this? We want to somehow simplify our shape, right? I mean, it's like a proof in graph theory, right? You just want to simplify the graph till it becomes easy to prove. Here it's a convex body. Okay. What can you do? So the main tool, and then this will be souped up very nicely, is called a bisection lemma. Okay, so it's a bisection or bisectional. And it says the following, that if I consider any n minus 2 dimensional subspace, okay, then orthogonal to it, right, there is a normal vector to hyperplane which bisects, let's fix one of these functions, g. All I'm trying to do is following. I'm trying to find a single hyperplane, so that the integral of g on this side is equal to the integral of g on the complement. Because if I do this, then this remains positive on both sides, and h must be positive on one of the two sides. And so we'll restrict attention to that half space. But nothing prevents us from doing this again and again and again, as long as we can find bisecting half spaces. Okay. Now, can we find bisecting half spaces? Yes, in fact, they're everywhere. Why is that? As long as you have a two-dimensional space in which you can move your normal vector, right? So imagine that you have a two-dimensional space in which you can move your normal vector. So in other words, the support is not yet one-dimensional already. It's at least two-dimensional, right? In that case, okay, here is the two-dimensional. I'm just drawing the possible normal vectors. Let me define a function here, which is just the integral of g on one side, this side, minus on the complement. Okay. Now, by the time, yeah, Prasad made the right gesture. By the time you move from here to the opposite side, the function value here is minus of the function value there, right? Because it just flips, which means what? As long as this is continuous, you will get a place where it's 0, and that's all we want to find. So if your support is two-dimensional, there will be a plane you can use to cut, and you maintain this, maintain this, maintain this. Okay, that sounds nice. Now, where do we stop? Right? How do we talk about this? So this is all the nice things that were done, and we can do that. Okay. So here's what we'll do. What we'll do is that for any subspace, n minus 2 dimensional subspace, which is defined by a rational. By that I mean, so to define a subspace, all I have to do is fix two coordinates, right? And as long as I can fix, there are rational interior points for a pair of coordinates, rational interior values for a pair of coordinates. I fix that, that gives me a subspace, and then I can do rotation, okay? So what we're doing now is we will consider this infinite sequence of bisections, but each one corresponds to a rational subspace. And we know that these can be enumerated. So the sequence is countable. So it can enumerate the sequence. And now, what is happening in the sequence? Let's consider the sequence of, let's say the original convex body was K, and we keep intersecting it with a sequence of hyperplanes, right? Okay. And this gives you smaller convex bodies. And now you have to argue that this sequence will reach a limit, okay? And this takes, a well-known theorem in analysis. No, because all you got is a half space, not a hyperplane. The dimension hasn't gone down. It's not clear. How do you go to n minus 1?
Even that
yeah.
At best, it seems.
No. The point is that if you're still at n minus 1, then there is a bisection still you can use.
That you will
yeah. And since it's a countable sequence, and as long as you have a two-dimensional support, there will be an interior point that's rational, and then you can bisect. So it's just a limiting argument that says that because you have used all rational points
in all directions,
in all exactly, yeah. So you get this intersection, and let me see if I can try to simulate this. Okay, so you have the board, I cut, right, and then cut again, and then I cut again, right, cut again. Now remember, the intersection remains convex because it's the intersection of half spaces, right, and then I cut again, and cut, right. This is as close to a director as I'll get, but this is okay. Here we go. And what's happening is that, the support is going to go to a one-dimensional. It's going to go to one-dimensional because it can't be two-dimensional. If it's two-dimensional, you can cut some more. Okay? That's the first step. So the support of this intersection of these convex bodies that we get here goes to either a point or an interval. Sorry? Well, we're bisecting, right? And we have strictly positive integrals. So you must have some support left. No, because then you can have a sequence. Once you have the sequence, then we can talk about a limit. No, finitely many will only give you something with volume still. No. We want to say that what's left is lower dimensional. Like the support itself is lower dimensional. Because remember, we're trying to get to something like this at the end of the day, that there is just, you don't need to worry about two-dimensional things. You only need to worry about one-dimensional functions, right? To prove. So this is the support part. But if you actually, we proved a lot more if you think about it, right? What we have here is, we're saying that you can restrict attention to an interval, fine, right? And then, orthogonal to this, what's happening? You're getting this convex body, right? That never cuts these points, of course, because we know that's the support in the end. But it gets closer and closer and closer and closer, right? So why do we have this waiting? Why don't we just say it's just the integral of the original function on this? The reason is this. Imagine it's getting closer at different rates. I mean, it looks like this, and the next time it looks like that, and it's always getting closer at a different rate. See, you're scaling down, but you're maintaining this rate. So the weighting is important. The weighting is preserved even in the limit. Okay? And this can be argued quite nicely, actually. Basically, you look at the sequence, and in the sequence, you define this, knowing with foresight that you will get this limit. You use the final, the limit part is easy to show, the support. Now you use that limit to say, let's go back and look at, in the sequence of bodies that I got, what is the intersection at every point along this? Okay, and then argue that this function of what I have here has some nice properties. First, it's concave, okay, and second, and therefore it's what's called equicontinuous. So the variation in the function is bounded by, it's kind of like Lipschitz basically, and then, but it only needs to be locally Lipschitz, and then as a result, there's a subsequence that converges, and so you immediately get that you have a concave to the n-1 weighting. Here we're saying linear. If you replace that with just concave to the n-1, then basically I've sketched the full argument. Except that the limit argument you need to use for the sequence of functions is called the Arzela-Ascoli theorem, equicontinuous function. No, it's equal. Sure, yeah. I mean, it's a countable sequence. The volume, I mean, original volume is still zero indeed, right? It's gone to a lower dimensional. What does, yeah. You can start with, I will start with a big ball that for which this is still true.
Why can't the limit? Yeah, the limit can be zero, but that I think is fixed by some other thing.
Yeah. We'll assume this is bigger than a strict epsilon if we want. Yeah. I prove it for that and then say that.
You do it for like G minus epsilon.
Exactly.
You do this argument for G minus epsilon.
Yes. Yeah. So what this will tell us is that you can use this to the times concave to the n-1. To go to linear takes more work. It's actually a very nice argument, combinatorial argument. I won't do that here. It's in the original paper. But also, we'll prove this theorem with only the concave version. We don't need the linear version. Okay. So still have 20 minutes, right? Oh, perfect. Yeah, that's a. Rational different. Yeah.
That is enough.
Yeah.
This is the part I always found.
Yeah. Okay, so imagine we did this and we did this and we did this, right? To this, and then at the end of the day, as a result, we got an interval, okay, and a weighting, right? Now, the weighting is coming from a convex body. So, in particular, what we got here is for our G and H, we say that the integral. So let me now think of the final interval, A, B, right? And I don't know what the weighting looks like. Okay, we don't know what the weighting looks like. There is A here, there's B here, and if I parameterize this by t, right, this is t equal to 0, this is t equal to 1, then at each point there is some weighting. Let me call that weight function f. Okay. In fact, I can call it f of t to the n-1, where f is concave. Okay. Since I used f for log concave, let me call it something else, psi t. Psi t to the n-1, where psi is concave actually. Why? If you take any convex body and I look at the cross sections, right, and I define the function at t to be the volume of this intersection, the volume of this k intersected with the plane here to the power 1 over n minus 1. This is a concave function. That's Brun-Minkowski. Okay? Because if you haven't seen the proof, this doesn't need localization. You just symmetrize, you replace the cross-section by a ball. The radius of the ball would be proportional to this. And then you argue that the radius must be a concave function because otherwise, the volumes would be violated. You use the Brun-Minkowski theorem there. Okay? That's the sense. So that's what this looks like. So now we going back here, we have a, b, and this concave function. And now I can look at it like this. I have a single interval 0 to 1. This is the interval for t. And let me define zi, subset of this, to be the set of points z belong to 0, 1, such that, or t belong to 0, 1, such that the point 1 minus t times a plus t times b belongs to Si. Right? I just want to see on this interval who is in S1, who is in S2, who is in S3. Right? So we're going back and mapping that here. So maybe this is in Z1 and this is in Z2 and so on. Okay? There could be multiple Z1s, because remember S is an arbitrary subset. S1 is an arbitrary subset here. And so we got this. Okay. So we have the, and what I have not marked is Z3. So now what do we need to prove now? We are saying that from this we get the same conclusion on the Z's. Right? The same conclusion holds on the Z. By the way, we've maintained the inequalities except for the weighting. So let's write it down. So it's saying that the integral over Z3 of this psi t to the n minus 1, right, is less than a times the minimum of integral over Z1 and integral over Z2 of the same psi t to the n minus 1, psi t to the n minus 1. Right? Because I combine the two inequalities again. Right? What this was saying that Z3 is less than Z1 and Z3 is less than Z2, that's what the min says. So to prove that their contradiction, we will just prove the opposite inequality. Right? So lemma, right? And in fact, in place of A, remember what is A? 2 times the distance between them divided by D. D, right, this is the distance between the intervals also now. And the D becomes 1 now, because we have scaled by it's A minus B is at most 1. So this is just 2 times distance between Z1 and Z2. Okay? And we will prove, this is what we will prove. And this will contradict this because this is at least as large as the original A, and we're done. Okay, how do we prove this? This is one-dimensional, right? How hard can it be? But you see, the Z's consist of many intervals and so on. So here is where you remember that Lowas and Shimowitz are combinatorials, right? Makes life so much easier for us. We can restrict attention to the case when Z1 is a single interval and Z2 is a single interval, and that's equally general. Why is that? And so here is this. I'm going to magnify the interval 0 to 1. Okay. Okay. Suppose we prove this for single interval Z1 and single interval Z2. That what's in between them is at least as large as these. Then I claim it's enough to prove it for everybody. So here's how you do it. You'd be a little bit careful because the Z's could be all over the place, right? They could be interleaved in funny ways. So here, let's say, is a particular Z1 interval and a particular Z2 interval. And we apply what we haven't yet proved. We'll prove that to these two intervals. And what we get is that what's in between them, right, is at least as large as either everything to the left or everything to the right, in fact, right? So either everything to the left is covered, right, or everything to the right is covered. And let's do this for every pair of intervals. Everything to the left or everything to the right is covered. Now, at the end of this, if all the intervals in Z1 are covered, you're happy. Or alternatively, if all the intervals in Z2 are covered, you're happy. But if that's not the case, that means there is some Z1 interval and some Z2 interval that are not covered. And you know the minimum distance between them is dZ1, Z2. You prove the inequality again and continue. Okay. So it's enough to focus on the case of one interval. Great. So now we have 1, 0 to 1. I might as well take this to be Z1 and this to be Z2. Okay? And I'm looking at this linear function to the n minus 1, which is not linear, concave function to the n minus 1, right? So it's some. In particular, concave to the n minus 1 is log concave. Concave functions are log concave, okay? It's still log concave. But it's unimodal, it can have only one peak and so on. So let's say this point is u, this point is v. This is a completely easy argument. So first claim is that there is going to be either u or v. Of course, one of them is less than or equal to the value, but also on one side, it's going to be non-increasing. So without loss of generality, we can assume that f of t, not f, side, so yeah, let me call f of t to be this psi t to the n minus 1. I'm just using log concavity, so that's why I'm calling it that. It's log concave. And now f of z for z less than or equal to u, less than or equal to f of u, which is less than or equal to f of b. This is what I want to say. Either this is true or the opposite is true, right? I mean, if this is not true, that means it's decreasing already at this point. And if it's decreasing here, it has to keep on decreasing. It can't go up again. So then it's going to be true on the right-hand side. So let's assume it's true on the left. Great. Now what are we left with doing? We put simple linear bounds on the two intervals. The distance, the integral from u to v, which is the z3 part, is at least the smaller value, f of u, times the distance between them. Right? Linear lower bound. And meanwhile, the integral from on z1 of f of t is at most the highest value, f of u, times the width of the interval, u, which is at most 1. So we're done. Right? So this is at least, no, are we done? Except for the factor of 2. So we proved here, this proves that integral over z3 is at least distance between z1, z2 times integral over z1. Right? We didn't prove factor of 2. That actually takes, you need to use the fact that it's linear to the n minus 1. And then you'll get it. You have to evaluate the integrals. So if you care about the factor of 2. Exactly, that's all unimodality. So in fact, for unimodality, you don't get 2. For log concavity, true is true.
It did not need linearity.
No, no. For that's why I said that even the weaker version that we actually established more almost formally is sufficient for this purpose. And for in many cases, though, it's very nice to have the more specific structure. In particular, Carberry Wright, for example, they use the linearity too, because there's a lot of cases to check. Yeah. Yeah.
So one sort of quantitative estimate that is used for the Brownian Kautsky.
Yes.
Is this sort of equivalent in the sense that can you prove the Brownian Kautsky inequality with just this
I don't know what that means because Brownian-Minkowski is a direct inductive proof. Yeah. 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 It's certainly Brownian-Minkowski becomes a one-dimensional thing. Yeah. I had in mind one other application straight from here, but maybe I won't write down so much so that there's a in the 10 minutes, but just want to mention it, and that's the, oh, so, sorry, any questions at this point before I do a variation? The max? So yeah, so let's see. No, not necessary. So suppose it's like this, then we're okay. If it's not like this, any point z, I mean t, I should say. Yeah. Yeah. So yeah. So the one possibility is that this starts decreasing like this. Right? You mean it goes up but then starts decreasing? But now you see, once it starts decreasing, it's decreasing completely on that side. So we have the property that this is smaller than this, as well as. Yeah. One of the two is smaller, and either the smaller one is already decreasing or the other one is decreasing. Yeah. This is probably a slicker way to say it, but. Yeah, because ultimately we're only using the entire width of the interval to bound the, in this case. Once you go to linear, of course, we know exactly what it happens, and then you just talk about. Yeah, you have to use the. Yeah. So there is another, yeah, there are, let's see, two quick things I wanted to mention here. One is that there is a, there are, as Piyush mentioned, equivalent versions. And these are proved to be equivalent in this paper by Kannan, Lovas, and Shimno. It's the same paper in which they introduced the KLS conjecture and proved the somewhat stronger versions of this theorem. But the equivalent version, it's nice. So what it gives you is that instead of these linear to the n-1 needles, you get what are called exponential needles. Okay, so exponential needle looks like this. It's defined by again an interval a b, 2 points, and a scalar gamma, real number, and then integral of a function over an exponential needle is integral from 0 to the length of the distance between a and b of, you know, f of the weight is exponential. Instead of linear to the n-1, it's exponential. So this is an exponential needle. You have to be a little bit more careful with exponential needles. You have to assume that the functions that you're playing with have compact support, which can typically be arranged. But otherwise, you get some nice conclusions. And there is one version which is convenient often, so I'll state that version. Equivalent again. You can state for linear or for exponential, but I'll state for exponential needles. And that says that suppose I have 4 functions, f1, f2, f3, f4, and these are just continuous. And I know, and then the following are equivalent. So the first one is, for every log concave f with compact support, the integral f1 is times integral f2 is less than or equal to integral f3 times integral f4. This is just product. So, okay. So suppose you have this. For every log concave, you want this to be true. I mean, that's a statement. This is equivalent to saying that for every exponential needle E, meaning for every A, B, gamma, just 3 things, we have integral over this exponential needle of ff1. Oh, sorry, there's no f anymore. ff1, f2, f3, f4. So we have replaced the arbitrary log concave function with an one-dimensional exponential function. Okay. This is often very convenient to use also. And in this paper, they show how you can derive this from low-Wallstrom limits. I'll prove that in the next lecture. Not equivalent. Stochastic will allow you to recover this.
Even though it's only a volume. The mysterious thing here seems to be this counting of direction. So how the, how the stochastic localization does that?
Yeah. How you drop dimension here. This is for all log concave F. These are arbitrary. Yeah, so this could be like the indicators of sets, for example. These don't have, these are just supposed to be continuous functions. So of course, indicators of sets, you have to smooth the boundary, but that's what you typically apply it to. Yeah, so these are kind of, things you want to use in your isoperimetry. So, yes, exactly, they're equivalent. So fix the functions. No, you don't fix F. You can't fix F. You have to argue about all log concave F. Yeah. But I mean, I think he's asking about the statement. So fix the functions, right? And suppose it is the case that these 4 functions satisfy this inequality for every log concave F. You want to verify this for whatever reason. You want to verify this. It's for any convex body. Yes. So, but the way we do it is for any convex body, yes, and for any partition, yes, exactly. Yes. So if you think about how we actually proved it, right? We proved it for any convex body, but we fixed the partition after we, the indicator functions of these sets, and then at the end we got it down to this nil. So again, it will be by contradiction. So suppose there is an F for which this is false. Then there will be an E for which this is false. So the F for which it's false is the convex body on which you assumed it's false. Yeah. Sure, yeah. No, I am. No, I think it's more like fix F1 squared. Then for all the person. Well, it depended in the sense that I mean, if I think of them as subsets of Rn, for example, I can fix them in advance. It doesn't really change the. So I see. So you should think of them as partitions of Rn. Yeah. Not K. I mean, you're just defining the function to be right? Because at the end, I'm going to multiply them. So even if F had been outside, it will zero out what's outside the set. Yeah. So this, for example, is a very convenient way to prove the strong log concavity isoperimetries, the ones about square root t for both the the Shiger isoperimetry and the log-Sokolov isoperimetry, because what you do is, that's what you want to prove, you formulate it like this, and then you say, I only need to consider exponential in one direction. Now, if I go down there, because I started with a strongly log concave measure, the measure is still strongly log concave, and I'm multiplying by exponential, that doesn't change anything. Exponential times Gaussian is still Gaussian. And so all I have to do is prove it for Gaussian, basically. And for Gaussian in 1D, these things are Gaussian restricted to an interval. That's the only slight challenge. It's not Gaussian arbitrary Gaussian, Gaussian restricted to an interval. And then you can work out by hand. And it turns out that for Gaussian, you actually get more than just the ratio. You get this square root log for small sets. Right? I mean, because if I look at the Gaussian value here, it's some e to the minus squared over 2, but the measure, I get this extra 1 over, whatever is the distance x, and that's what contributes to it. Yeah, so many of the theorems I stated are proven by just this, including some on that side. Yeah, maybe it's a good time to break, and when we come back, I'll switch to the modern extension of this localization. Sorry? Yeah. Why does it show up? Yeah, I mean, yeah, it's a good question. I mean, so the way it's shown is that you can take this linear to the n-1 and approximate it by an exponential. And in fact, it preserves the linear to the n-1. The needles are arbitrarily long, but a linear function to the n-1, for the purpose of these integrals, we can also replace with an exponential function. Yes. And so for inequalities for which something is true for exponential functions, there is no n anymore in the expression. In fact, there is a nice way to view this. This was a view that came up later by Fradelisi and Guedin, and they proved that, basically they reinterpreted this as saying the following. Suppose I look at all log concave measures in measure space, so there's 1 point per log concave measure, and these measures all satisfy some inequality, like the integral of f over the measure is non-negative. Now, in this set, which is a convex set, because convex combinations are still log concave measures, what are the extreme points? And they proved that the extreme, using localization, the extreme measures on this, in this convex hull of all log concave measures that satisfy inequality are exactly exponential needles or single points, Dirac measures. So that's very nice, because now if you want to understand the minimum of some convex function over measures, you just need to look at the minimum over exponential measures. This equivalent. Yeah.
But then this extreme points not the linear.
Right. But nevertheless, sometimes if there's a dimension dependence, linear is a nice way to.
So these are not dimensions. So the predicate is.
It's exponential needle, so you get the exponential needle. So whatever is true, yeah. Once you go to exponential needle, there's no dimension, right? It's just, yeah.